Physics-informed UNets for discovering hidden elasticity in heterogeneous materials introduces a novel neural network model, El-UNet, designed to estimate the spatial distributions of mechanical parameters from strain maps, normal stress boundary conditions, and domain physics information. This model outperforms fully connected physics-informed neural networks in terms of accuracy and computational cost in isotropic linear elasticity inversion problems. The proposed El-UNet leverages the convolutional neural network architecture to effectively capture spatial correlations in material properties, making it an efficient tool for solving three-dimensional inverse elasticity problems. The paper also presents various variations of El-UNet and proposes a self-adaptive spatial loss weighting approach that significantly improves the model's performance. To validate the inversion models, the authors conducted finite-element simulations of isotropic domains with heterogeneous distributions of material parameters, generating synthetic data for testing. The results show that El-UNet is not only faster but also more accurate than fully connected physics-informed neural networks in resolving the distribution of unknown fields. Among the tested models, the self-adaptive spatially weighted models achieved the most accurate reconstructions in equal computation times. The learned spatial weighting distribution visibly corresponded to regions that the unweighted models were resolving inaccurately. This research demonstrates a computationally efficient inversion algorithm for elasticity imaging using convolutional neural networks, offering a potential fast framework for three-dimensional inverse elasticity problems that have proven unachievable through previously proposed methods. The study contributes to the advancement of model-based elastography, elasticity imaging, deep learning, and tissue biomechanics. Elasticity imaging is a technique used to reconstruct the spatial distribution of mechanical properties from available deformation and force measurements. However, this problem is inherently ill-posed due to the inability to measure the stress distribution inside the domain. Various methods have been introduced to solve the inverse problem, including the use of neural networks with physics-based loss functions. Physics-informed neural networks, PIN, methods employ fully connected feed-forward networks to estimate mechanical parameters and stress fields by taking spatial coordinates as inputs. The outputs are then used to construct physics-based loss functions, which involve partial derivatives of mechanical stress computed using automatic differentiation or alternative methods. However, fully connected networks are not the most efficient choice for learning from spatially structured data, as they take a long time to learn complex spatial patterns and become increasingly costly to train for deep networks or large datasets. Convolutional neural networks, CNNs, on the other hand, are well suited for tasks that require processing spatially structured data, and physics-informed models with CNNs and UNet structures have been successfully applied in various fields. UNets have been used as a super-resolution tool, conserving equilibrium constraints, and have shown great efficiency in learning directly from physics data when coupled with vision transformers. To the best of our knowledge, UNets have not been used to directly solve inverse problems in elasticity using only physics constraints. Therefore, we propose El-UNet, an inversion physics-based neural network model based on the UNet encoder-decoder structure, to solve inverse problems in linear elasticity. Our model takes normalized strain distributions as input images and boundary and loading conditions as additional inputs to reconstruct material parameter and stress distributions. The use of El-UNet in elasticity imaging can provide a robust tool for characterizing tissues across multiple scales, particularly in brain tissue, which is comprised of many tissue subtypes with varying material properties and complex geometrical patterns. We propose several El-UNet implementations, including two with self-adaptive spatial loss weighting methods, for estimating isotropic linear elasticity parameters in a heterogeneous 2D example. These models are compared to a fully connected, dense, PIN implementation under equal circumstances. The performance of the models is demonstrated on three embedded brain tissue examples with distinct elastic modulus and Poisson's ratio assignments for white matter, gray matter, and the background. These benchmarking examples reveal the robustness of the tested models against various characterization scenarios. The El-UNet architecture is detailed, including its encoder-decoder network with 5 levels, increasing in number of channels from 64 to 1024. The network outputs enter physical and boundary mean squared error loss equations, and the atom optimizer updates the network parameters. The elasticity equation is formulated in index notation and reduced for isotropic linear elasticity in 2 dimensions. The Lamé parameters and their conversion to elastic modulus and Poisson's ratio are discussed. The static equilibrium equations are also presented, and their dimensionless variation is used in the inversion algorithm. The research discusses the application of dimensionless values for analyzing brain tissue under tensile loading. It presents a finite-element simulation of a brain slice, where a T1 weighted image is used to segment gray and white matter. The simulation involves a uniform normal stress applied from the top, with the bottom side as a frictionless boundary. The background material is softer than the brain tissue, with elastic parameters varying for white and gray matter. The study also explores the robustness of the models by adding Gaussian noise to the strain data. The results are compared against ground truth, showcasing the performance of the models in various scenarios. The research emphasizes the importance of accurately resolving the distribution of patterns in brain tissue for elasticity imaging. It concludes by highlighting the potential of the dimensionless approach for more complex heterogeneous patterns and inclusions. The research paper discusses the development of El-UNet, an encoder-decoder structure based on the original UNet architecture, to solve the inverse problem in quasi-static elasticity imaging. This novel approach aims to estimate the spatial distribution of the Lamé parameters and stress distributions from strain fields obtained through finite-element analysis. Figure 2 illustrates the breakdown of finite-element derived strain fields and parameter distributions used as input and validation data for the inverse models. These inputs are crucial for the El-UNet model to accurately predict the Lamé parameters and stress distributions. On page 10, the authors detail the implementation of El-UNet, which takes a 3-channel input containing normalized spatial distributions of a strain tensor term. The network estimates either dimensionless Lamé parameters only, PEL-UNet, or Lamé parameters and stress distributions together, PSEL-UNet. The 2 main UNet setups used in this study are shown in Figure 3. The primary difference between them lies in the output channels. For PEL-UNet, the algorithm utilizes isotropic linear elasticity constitutive equations to compute stress terms across the domain using the estimated Lamé parameters and given strains. It then computes the mean squared error, MSE, loss values for static equilibrium in 2 directions and normal stress on the boundaries. The partial derivatives in the static equilibrium equations are approximated as finite central difference inside the domain and forward-backward difference on the boundaries. Following the dimensionless approach, the spacing for the central difference approximation is computed as. In the context of physics-informed neural networks, PINNs, the proposed models aim to enhance the estimation of Lamé parameters in linear elasticity problems. The research focuses on 2 main objectives: developing a novel neural network architecture called El-UNet, which is designed for solving inverse elasticity problems, and introducing self-adaptive spatial loss weighting methods to improve the convergence and accuracy of the model. The El-UNet model combines the strengths of both physics-informed neural networks and UNet architectures. It consists of an encoder and a decoder part, with skip connections between them to preserve spatial information. The model uses a multi-scale approach by incorporating both fine and coarse scales in its architecture, allowing it to capture both local and global features of the input data. To further enhance the performance of the El-UNet model, 2 self-adaptive spatial weighting methods were introduced, PSEL-UNet W1 and PSEL-UNet W2. These methods involve creating trainable weight fields that adapt during training to emphasize regions with higher errors in the loss functions. In PSEL-UNet W1, spatial weights are applied to all loss terms, including constitutive equations, static equilibrium, and boundary conditions. In contrast, PSEL-UNet W2 does not apply weighting to the static equilibrium loss term. By comparing these 2 variations with the non-adaptive El-UNet model under equal computational cost circumstances, the potential accuracy gain can be assessed. A dense pin implementation was also compared to demonstrate the improvements achieved by the proposed models. This comparison involved constructing networks and training pipelines as described in a previous study, using the same resolution of input and boundary condition data as the UNet models. All models were implemented in PyTorch version 1.13.1, with the Atom optimizer used to minimize the loss functions at a learning rate of 0.001 without any decay settings. Overall, the research presents a novel neural network architecture and self-adaptive spatial loss weighting methods aimed at improving the estimation of Lamé parameters in inverse elasticity problems. By leveraging the strengths of both PINNs and UNets, the proposed models offer a promising approach for solving complex physics-based problems efficiently and accurately. Here is the combined summary. The researchers trained each model for 30 minutes on NVIDIA P100 GPUs, evaluating the loss value and performing each run 10 times to account for the oscillatory nature of loss evolution during training. The network state was initiated randomly, resulting in a small variance in the number of epochs performed during each run. To compare weighted and non-weighted models, the loss associated with the physical equations in their non-weighted state was reported. The study investigated 4 physics-informed inversion models, described in Table 2, dense pin, El-UNet, El-UNet, and 2 spatially weighted variants of El-UNet, denoted as W1 and W2. The UNet architectures were found to generally provide more accurately resolved estimates compared to dense pin. The visual depiction of estimated fields revealed that the 2 output implementation of dense pin exhibited visible artifacts, especially for the new estimation. In contrast, the 5 output implementation did not show these artifacts but appeared less accurate in terms of overall discovered patterns. The 2 spatially weighted implementations, W1 and W2, provided the closest estimation to the ground truth with minimal artifacts. Figure 5 illustrates the estimation and absolute relative error maps from the various physics-informed models under study for the soft background example. The qualitative evaluation of estimated maps reveals improved estimation of El-UNet models compared to dense pin. The weighted UNet models, namely W1 and W2, show the best results for both E and Nu. In the inverse run with noisy strain data, the UNet models resolved a grainy reconstruction of the unknown parameters, as shown in Figure 6. While the pin model produced less grainy outputs, it did not resolve the pattern as thoroughly as the UNet models. Here is the combined summary. The physics-informed models under study are evaluated for their performance in estimating unknown parameters in the soft and stiff background examples. Figure 6 presents the estimation and absolute relative error maps for the soft background example with noisy strain inputs, revealing that the dense pin model provides less accurate and grainy reconstruction compared to unweighted UNet models. In contrast, the weighted and unweighted El-UNet models demonstrate more robustness against noise. The stiff background example, as shown in Figure 7, exhibits poor reconstruction of unknown parameters, particularly in the transition zone between the background and gray matter, where El-UNet W1 outperforms other models. To quantify model performance, the evolution of total loss and mean estimation errors are compared between models in Figure 8. The results indicate that both the 2-output network, El-UNet, and the 5-output network, El-UNet, outperform the dense pin in E-estimation accuracy, with El-UNet exhibiting better VV estimation. The self-adaptive weighted El-UNet models, specifically El-UNet W1, show improved performance in capturing complex patterns while minimizing reconstruction artifacts. Notably, the stiff background example poses significant challenges to the models, with the transition zone between the background and gray matter being particularly difficult to reconstruct. The El-UNet models, however, demonstrate improved robustness in this region, highlighting their potential for accurate estimation of unknown parameters in complex scenarios. The analysis of the El-UNet configurations reveals distinct estimation error trends for W1 and W2. Notably, W1 exhibits decreasing or plateauing errors across epochs, whereas W2 displays a reversal in the error trend for VV estimation, particularly pronounced in noisy strain and stiff background examples. Figure 8 illustrates the total training loss and mean absolute relative errors, showcasing the reliable loss and error evolution trend of El-UNet W1. The self-adaptive spatial loss-weight distributions, learned from the different examples, provide insight into the improved performance of the weighted models. The final spatial distribution of loss weights, visualized in Figure 9, indicates that the model assigns more weight to regions with higher loss values, corresponding to the constitutive equations, PSPC, static equilibrium, PSPZ, and boundaries, PSP sides and PSP's top-bottom. This adaptive weighting enables the model to penalize itself more heavily in regions where physical constraint violations are most pronounced during training. The learned spatial loss weights demonstrate that the model effectively captures the underlying physics of the problem, focusing on areas where the constitutive equations, static equilibrium, and boundary conditions are most critical. The constitutive equations weight, PSPC, and boundary weights, PSP sides and PSP's top-bottom, are plotted with a pixel offset around the PSPC map, revealing a nuanced understanding of the problem's spatial complexity. By adaptively weighting the loss terms, the model can better navigate the complex interplay between physical constraints, leading to improved performance and robustness. Here is a combined summary of pages 19 and 20 of the research paper. The paper introduces UNet-based models, collectively named El-UNet, for inverse reconstruction of material properties from strain fields and boundary conditions in elasticity imaging. The authors compare the performance of different variations of these models for 2D plane stress examples with their previous model, which used densely connected physics-informed neural networks, PIN. The results show improved reconstruction by the UNet-based models, with the spatially weighted models exhibiting the best performance. The weighted models are the fastest and achieve the lowest estimation errors among the tested models under similar computational time circumstances. The final weight distribution indicates the areas the model learns to penalize itself more while training, and tracking the error decay patterns across epochs reveals that the weighted models reach the lowest estimation errors and effectively discover complex patterns much faster than the alternatives. The encoder-decoder structure and convolutional nature of the UNet show advantages over fully connected implementation of PIN, as the convolution kernels share weights for different parts of the image and recover patterns better, making them ideal for spatially structured data such as images and volumes. Comparing PIN with El-UNet and El-UNet clearly shows El-UNet's superior performance in resolving accurate distribution of unknown parameters in a relatively short estimation time shared between all models. The improvements are evident in successful reconstruction of sharp gradients between different regions of the image. The authors also compare the performance of El-UNet and El-UNet, which differ in their output type. El-UNet estimates the unknown parameter distributions and plugs those values, along with strains, into the constitutive equations to compute stress distributions. In contrast, El-UNet becomes better regularized by enforcing the constitutive equations as soft constraints, leading to improved performance. The introduction of self-adaptive spatial loss weights with two proposed weighting schemes further improves the convergence of the UNet-based models. The results show that both weighted implementations visibly lead to better reconstruction than the unweighted approaches. The final distribution of spatial loss weights reveals the increased intensities corresponding to regions where the model learns to penalize itself more, which overlap with high estimation error regions of the unweighted El-UNet model. The research paper discusses the development of a novel physics-informed neural network model, El-UNet, for solving the inverse elasticity problem in medical imaging. This model utilizes spatial loss weighting to enhance accuracy and efficiency in estimating tissue elasticity. Unlike previous studies that require additional backpropagation for optimizer updates or have been tested only in fully connected networks, El-UNet's self-adaptive spatial loss weighting method does not require extra deep networks and thus maintains computational efficiency. El-UNet works with isotropic spatially structured data, which is common in elastography images. However, it can be adapted to handle anisotropic resolutions from ultrasound and magnetic resonance images by adjusting differentiation intervals in the finite difference computation stage. The model uses the simplest approximation for partial derivatives in static equilibrium equations, which may lead to error amplification in some variations. Alternative implementations have been proposed to pose these equations as convolutional layers, potentially avoiding error accumulation. The study also highlights the potential for scaling up to 3D estimations and other material models, such as multi-parameter orthotropic elasticity or hyperelasticity, relevant in biological tissues. Future work includes applying the main ideas presented in this study to these more complex problems. This research was supported by the National Institutes of Health, NIH, National Institute of Biomedical Imaging and Bioengineering, NIBIB, Trailblazer Award number R21EB032187. The authors declare no conflict of interest. Here is the combined summary of pages 23 and 24. Physics-informed neural networks, PINNs, have been widely applied in various fields, including materials science, biomechanics, and computer vision. Recent studies have utilized PINNs to analyze internal structures and defects in materials, elasticity imaging, and predicting temperature fields. These approaches leverage the strengths of both physics-based modeling and machine learning to solve forward, inverse, and mixed problems. In the context of elasticity imaging, researchers have employed PINNs to spatially discover elastic modulus and Poisson's ratio, as well as to predict 2D stress tensor fields conserving equilibrium constraints. Furthermore, PINNs have been used for high-dimensional surrogate modeling and uncertainty quantification without labeled data. In addition, the concept of physics-constrained deep learning has been extended to convolutional neural networks for image segmentation and temperature field prediction. More recently, the vision transformer operator, VITO, has been proposed, which integrates the strengths of both vision transformers and physics-informed operators. In the field of biomechanics, researchers have focused on non-invasive imaging of Young's modulus and Poisson's ratio in cancers in vivo, as well as on finite compression of brain tissue. Constitutive models for brain tissue have been developed, and numerical methods have been reviewed for finite-element modeling of traumatic brain injury. Biomechanical modeling and computer simulation of the brain during neurosurgery have also been explored. Theoretical foundations of elasticity theory, numerical methods, and computer simulations are essential for understanding and predicting the behavior of complex systems. UNets, a type of convolutional neural network, have been widely used for biomedical image segmentation. Self-adaptive weight physics-informed neural networks have been proposed for non-Fourier heat conduction. Finally, researchers have investigated the understanding and mitigation of gradient flow pathologies in PINNs, as well as the neural tangent kernel perspective on pin training failures. Here is the combined summary of pages 25 and 26. The authors draw upon previous works that have successfully employed physics-informed neural networks, PINNs, to solve various types of partial differential equations, PDEs. Specifically, they cite studies that have applied PINNs to continuum micromechanics, solving parameterized steady-state PDEs on irregular domains, and tackling problems in computational physics. These approaches have demonstrated the potential of PINNs in capturing complex nonlinear relationships between physical variables. The proposed methodology, dubbed Phi-CR-Net, integrates the strengths of PINNs and graph convolutional neural networks, GCNNs, to address the challenges of solving PDEs on complex geometries. Phi-CR-Net's architecture consists of three primary components: a physics-informed neural network, a graph convolutional neural network, and a geometry adaptive module. The physics-informed neural network ensures that the solution satisfies the underlying PDE, while the graph convolutional neural network leverages the graph structure of the discretized domain to capture local and global patterns. The geometry adaptive module enables the network to adapt to varying geometries and boundary conditions. The authors present the Phi-CR-Net algorithm, which involves minimizing a loss function comprising two components: a PDE residual term and a boundary condition term. The PDE residual term measures the difference between the predicted solution and the actual solution, while the boundary condition term enforces the satisfaction of boundary conditions. The algorithm is illustrated in equation 1, where the loss function is defined as the sum of the PDE residual and boundary condition terms, weighted by hyperparameters alpha and beta, respectively. The authors also provide a visual representation of the Phi-CR-Net architecture in Figure 1, which illustrates the flow of information between the three components. The graph convolutional neural network takes the graph's structured data as input, while the physics-informed neural network and geometry adaptive module process the output to generate the final solution.